Let the day grow quieter now, as though a distant door has gently closed behind you. Imagine entering an ancient workshop, warmed by small oil lamps and the fading light of evening. You can hear water moving through a narrow channel outside. Somewhere nearby, a wooden wheel turns slowly, while stone and metal tools make soft, patient sounds. Nothing here is hurried, and nothing needs your attention. You may simply rest while the old workshop continues its quiet work around you. On a wooden table lies a small arrangement of bronze wheels, each one cut with carefully spaced teeth. They belong to a remarkable device, now called the Antikythera mechanism. Greek craftspeople built this complex instrument more than 2,000 years ago. Its surviving fragments were discovered in an ancient shipwreck near the island of Antikythera. Inside the device, many interlocking gears represented cycles in the sky. Turning a handle allowed its dials to display astronomical information and calendar patterns. It could track the movements of the sun and moon. Some displays also represented eclipses and the timing of important Greek festivals. Researchers have studied the corroded fragments using X-rays and detailed imaging. These methods revealed hidden inscriptions and gears that could not be seen from the surface. The complete appearance of the mechanism remains partly uncertain. However, the evidence clearly shows a sophisticated tradition of Greek mechanical astronomy. Perhaps similar instruments once existed in other workshops and libraries. Most would have been melted down, damaged, or lost during the passing centuries. For tonight, you do not need to remember every gear. You can let the bronze wheels turn quietly somewhere beyond your thoughts. Farther west, Roman builders were mixing lime, water, stone, and volcanic material. Their concrete became one of the foundations of Roman engineering. The mixture was not identical to modern concrete. Roman builders adjusted their materials according to the structure and the resources available nearby. Around the Bay of Naples, volcanic ash called pozzolana helped create durable concrete. It could harden even when used in wet coastal environments. This made it valuable for harbors, breakwaters, and other structures exposed to seawater. Some Roman marine concrete has survived for nearly 2,000 years. Scientists continue studying the chemistry behind its long durability. Reactions involving volcanic material in seawater appear to have strengthened parts of the concrete over time. This does not mean Roman concrete was always superior to modern materials. Different concretes were designed for different conditions, loads, and construction methods. Roman builders also used concrete inside walls, vaults, and enormous domes. Brick or stone often formed the visible surface around the concrete core. In the quiet of a building site, workers carried baskets of aggregate and mixed heavy materials by hand. Every wall rose through repeated movements performed across many calm working days. Water was another material shaped by ancient engineering. Roman aqueducts carried it from springs and distant landscapes toward towns, farms, fountains, and public baths. Many aqueduct channels relied on gravity rather than mechanical pumps. Their slopes had to be gentle enough to prevent damaging currents. Surveyors measured the land using simple but effective instruments. One device, the chorobates, helped builders check whether a surface was level. It was a long wooden frame fitted with plumb lines. When wind disturbed the hanging cords, water in a groove could provide another level reference. Another surveying tool was the groma. Its crossed arms and hanging lines helped establish straight roads, right angles, and orderly building layouts. These instruments were made from ordinary materials, yet they supported large engineering projects. Their usefulness came from careful observation and repeated measurement. Aqueducts were not always carried on tall arches. Much of their length usually ran underground or close to the surface. The famous rows of arches were needed where channels crossed valleys or uneven ground. They maintained the gentle slope while allowing roads and streams to pass below. Maintenance workers entered channels through access points and removed mineral deposits. Without regular care, even the finest water system could slowly lose its usefulness. There is no need to follow every channel tonight. Let the water continue flowing softly through the darkened hills. Long before Roman aqueducts, farmers in many regions had learned to guide water across dry land. Irrigation supported settlements in Mesopotamia, Egypt, the Indus region, China, and elsewhere. Canals carried river water toward fields where rainfall alone was unreliable. Smaller channels then divided the flow between crops and neighboring communities. Managing irrigation required more than digging trenches. People had to observe seasons, repair banks, clear silt, and agree upon shared water schedules. In ancient Egypt, the yearly movement of the Nile shaped agriculture. Basin irrigation stored floodwater temporarily before allowing it to soak into the soil. Farmers also used devices called shadus in later ancient periods. A long pole, balanced on a support, lifted a water container with reduced effort. A counterweight helped raise the filled container from a river or canal. The water could then be poured into a higher irrigation channel. The idea was simple and practical. It transformed the lifting of water into a slow rhythm of balance, weight, and human movement. Another water-lifting device is associated with Archimedes, the Greek mathematician and engineer. The Archimedes screw contains a spiral surface inside a cylinder or surrounding a central shaft. As the screw turns, pockets of water travel upward along the spiral. The device can lift water from a lower level to a higher channel. Its precise origin remains uncertain, and similar concepts may have existed earlier. Ancient writers connected the device with Archimedes during the 3rd century BCE. Versions of the screw were used for irrigation and drainage. The same basic principle still appears in some modern pumps and industrial systems. Imagine the wooden cylinder turning beside a quiet field. Water rises gradually, shining for a moment beneath the evening sky. In the cities of the Indus Valley civilization, water management took another impressive form. Settlements such as Mohenjo-Daro and Harappa included carefully planned wells and drainage systems. Many houses had access to bathing areas or nearby water sources. Brick-lined drains carried wastewater away from living spaces. Some drains were covered with removable slabs. This design allowed sections to be opened for cleaning and maintenance. The systems were not modern sewers in every sense. Yet archaeological evidence shows that sanitation and controlled drainage were important parts of urban planning. Standardized baked bricks helped builders create regular walls, platforms, and channels. Their consistent proportions made them useful across many construction tasks. The exact organization behind these cities remains partly uncertain. Their script has not yet been reliably deciphered, leaving many questions about administration and daily life. Still, the streets and drains reveal careful planning. They suggest communities that valued water, cleanliness, reliable construction, and long-term maintenance. You can let these ancient streets grow quiet now. the covered drains remained beneath them, carrying a faint stream into the peaceful night. Across all these places, technology began with close attention to ordinary things. People watched water flow, shadows move, weights balance, and materials change inside fire. They tested what worked, remembered useful methods, and taught them to others. Improvement often came through generations rather than one sudden moment of invention. If your eyes feel heavy, you can let them close. The quiet workshops of the past will keep moving softly in the background. Along an ancient road, the night settles gently over rows of fitted stones. A cart passes slowly, its wooden wheels following grooves worn by many journeys. Road building was one of the most important technologies of the ancient world. Reliable routes connected farms, ports, towns, temples, and distant markets. Roman roads are especially well preserved in some regions. Their construction varied, but many included compacted earth, gravel, drainage layers, and carefully placed paving stones. The surface was often slightly raised in the center. Rainwater could move toward ditches instead of collecting beneath passing feet and wheels. Surveyors tried to keep major roads direct when the landscape allowed it. Hills, rivers, marshes, and existing settlements still required many practical adjustments. Milestones marked distances and sometimes named officials responsible for construction. Travelers could estimate how far they had come and how much road remained. Other civilizations also created extensive road networks. The Persian Royal Road linked important centers across the Achaemenid Empire and supported regular communication. In South America, Andean peoples developed mountain roads long before European arrival. Later, the Inca expanded these routes across steep and difficult terrain. Stone steps, retaining walls, and suspension bridges helped travelers cross high landscapes. Pack animals and human messengers moved along routes where wheeled carts were often impractical. The materials changed from region to region. The underlying idea remained simple: shape the land so movement becomes safer, steadier, and more predictable. You do not need to follow every road tonight. Let each one disappear quietly beyond the next hill. Where roads met rivers, ancient engineers built bridges from timber, stone, rope, and brick. Their designs depended on local materials and the strength of the current. Stone arch bridges were especially durable when built on firm foundations. The curved arch directed weight outward and downward into supporting piers. Each arch was first shaped over a temporary wooden framework. Wedge-shaped stones were placed until the central stone locked the structure together. When the wooden support was removed, the arch carried its own weight. The stones pressed against one another, creating a stable form without modern steel reinforcement. Roman builders used this principle in bridges and aqueducts. Similar arch traditions also developed in ancient Mesopotamia, Persia, China, and other regions. Bridges needed protection from moving water. Piers were sometimes shaped to reduce the force of the current and guide debris around them. Floods and shifting riverbeds remained constant challenges. Many ancient bridges were repaired, rebuilt, or replaced over centuries. Their survival was rarely the result of one perfect construction moment. It often depended on generations of maintenance and local knowledge. Imagine the sound beneath a stone bridge after sunset. The water continues under the arches, while the road above grows still. Nearby, a building site is quieting for the evening. A wooden crane stands against the sky, with ropes hanging loosely from its beam. Greek and Roman builders used cranes to lift heavy stone blocks. These machines combined levers, pulleys, ropes, and human or animal power. A simple pulley changed the direction of force. Multiple pulleys could create mechanical advantage, allowing a smaller force to lift a greater load. Some cranes included tread wheels large enough for workers to walk inside them. Their weight turned the wheel and slowly wound the lifting rope. The load still had to remain within safe limits. Rope strength, timber quality, balance, and communication were all essential. Stone blocks were prepared with lifting points or special holes. Metal clamps, tongs, and ropes helped workers guide them into position. The exact arrangement differed between workshops and periods. Archaeologists study tool marks, unfinished buildings, written descriptions, and surviving hardware to understand these methods. Lifting a block was only part of the task. Builders also needed to rotate, align, and lower it without damaging the stone beneath. Small adjustments could be made with wooden levers. Thin layers of mortar or carefully dressed surfaces helped the stone settle evenly. There was no need for the crane to move quickly. Its strength came from controlled motion, repeated effort, and patient coordination. Let the ropes hang quietly now. The final stone of the day has already been placed. In ancient Egypt, stoneworking produced temples, statues, sarcophagi, and monuments whose surfaces still preserve tool marks. Craftspeople worked with copper, bronze, stone, sand, and wooden equipment. Hard stones, such as granite, required long and demanding labor. Researchers have found evidence for pounding with durable stone tools and cutting with abrasives. Copper saws and drills may have been used with quartz-rich sand. The abrasive particles performed much of the cutting as the tool moved repeatedly. The exact methods used for some individual objects remain under study. Experiments help researchers test how quickly different tools and abrasives could shape stone. Ancient workers were not using mysterious, unknown machines. They combined available materials with time, organization, and highly developed skill. Straight lines could be marked with chords. Surfaces could be checked with squares, levels, and simple measuring rods. The Egyptian cubit was divided into smaller units. Standard measuring rods helped maintain proportions across construction and craftwork. Plumb lines showed vertical alignment through gravity. A weighted cord could reveal whether a wall or column leaned away from true vertical. For horizontal measurements, builders used water and simple leveling devices. The still surface of water provided a dependable reference. These tools were modest, but precision does not always require complexity. A reliable reference, used carefully, can guide a very large structure. Large monuments also required planning beyond the stone itself. Workers needed food, shelter, transport, tools, schedules, and access to quarries. Archaeological evidence from worker settlements shows organized communities near major construction sites. Skilled laborers, craftspeople, and support workers all contributed. Moving heavy stone probably involved sledges, prepared paths, ropes, and coordinated teams. Wetting sand may have reduced resistance in some transport conditions. The exact methods differed according to the stone, route, and project. Researchers continue comparing physical evidence with experimental reconstructions. There is no need to solve every ancient construction question tonight. It is enough to picture many careful hands working beneath a pale morning sky. Far from the quarries, metalworkers tended furnaces whose glow changed the color of the workshop walls. Their craft depended on controlling heat without modern thermometers. Bronze is usually an alloy of copper and tin. It could be harder than pure copper and was useful for tools, vessels, fittings, and decorative objects. Producing bronze required access to ores that were often found far apart. Trade networks carried metals across long distances between mining regions and workshops. Craftspeople learned how different mixtures behaved. Too much or too little of one ingredient could affect hardness, color, and ease of casting. Molten metal was poured into molds made from stone, clay, or other materials. Some objects were cast in several parts and joined afterward. The lost wax process allowed more complex shapes. A wax model was covered in a heat-resistant material, then heated until the wax drained away. Molten metal filled the empty space left behind. After cooling, the outer mold was removed and the surface was finished by hand. Iron production required another kind of knowledge. Early furnaces usually did not melt iron completely, but produced a spongy mass called a bloom. The bloom contained iron mixed with slag and other material. Repeated heating and hammering helped remove impurities and consolidate the metal. Carbon could enter the iron during heating, changing its properties. Ancient smiths learned through experience how fire, fuel, time, and hammering affected the result. Methods varied widely across Africa, Europe, Asia, and the Middle East. Different furnace designs reflected local ores, fuels, climates, and traditions. Some ancient steels achieved impressive quality. Their production still depended on careful process control rather than secret, impossible technology. Listen for the gentle rhythm of the hammer, growing more distant now. The furnace remains warm, but the workshop is settling into rest. There is no need to remember each material or method. You can let the old roads, bridges, cranes, and furnaces drift softly past you. In another quiet workshop, pale sand rests beside bowls of mineral powder and crushed stone. A small furnace glows steadily, waiting for glass to soften. Early glassmaking developed gradually across parts of Mesopotamia and Egypt. At first, glass was often used for beads, inlays, small vessels, and decorative surfaces. Glass forms when silica is heated with materials that lower its melting temperature. Ancient craftspeople often used sand or crushed quartz, mixed with plant ash or mineral soda. Color came from added metals and other compounds. Copper could produce blue or green tones, while different ingredients created amber, purple, white, or dark glass. The exact recipes varied between regions and workshops. Temperature, furnace atmosphere, raw materials, and repeated heating all influenced the final result. Early vessels were sometimes formed around a temporary core. Hot glass was wound or shaped around the core, then decorated with trails of contrasting color. After cooling, the inner material could be removed. The vessel remained as a small hollow container with a carefully worked surface. Later, glassblowing transformed production in the Eastern Mediterranean. A craftsperson gathered molten glass onto a hollow tube and gently introduced air. The glass expanded into a bubble that could be shaped with tools and gravity. This method made vessels faster to produce and allowed many new forms. The work still required close attention. Glass can become too cool, too soft, too thin, or uneven within moments. Imagine the orange glow reflected in a darkened room. A small glass vessel turns slowly at the end of a pipe. There is no need to follow every movement. You can let the warm light remain while the details drift away. Near the water, another group of craftspeople prepares timber for a ship. The scent of wood, rope, resin, and salt fills the evening air. Ancient shipbuilding was never one single tradition. Egyptian riverboats, Phoenician merchant ships, Greek vessels, Roman cargo ships, Indian ocean craft, and Chinese ships developed differently. Builders selected wood according to strength, flexibility, availability, and resistance to decay. Planks had to fit closely enough to withstand long contact with water. Some Mediterranean ships used mortise and tenon joints. Wooden tongues fitted into matching slots and were secured with pegs. This joined neighboring planks into a strong shell. Internal frames could then support and reinforce the completed hull. Other traditions began with frames before adding outer planking. Some vessels used sewn construction, with planks fastened using cords through prepared holes. Waterproofing materials helped seal joints. Resins, waxes, oils, fibers, and natural compounds were used according to local practice. Shipwrights worked without modern digital plans. They relied on measuring chords, templates, remember proportions, and knowledge passed through apprenticeship. The curve of a hull had to balance many needs. It required stability, cargo space, speed, maneuverability, and enough strength for waves. Ancient sailors also learned how sails responded to changing wind. Square sails worked well with favorable winds, while other rigs allowed different handling. Oars remained important in many vessels. On rivers, in harbors, or during calm weather, human power could move a ship with steady rhythm. Large cargo ships carried grain, oil, wine, stone, metals, timber, pottery, and countless ordinary goods. Their technology connected communities, separated by wide stretches of water. Archaeologists learned from shipwrecks preserved beneath sediment. Timbers, fasteners, cargo, tools, and repairs reveal how vessels were built and used. Many details remain incomplete because wood usually decays. Each surviving hull offers only one quiet part of a much larger history. Let the harbor grow still now. The ropes are tied, the sail is lowered, and the hull moves gently against the pier. Far beyond the harbor lights, sailors watch the sky. Navigation by stars was among the most enduring technologies of the ancient world. People noticed that some stars rose and set at predictable times. Others seemed to circle around a fixed region of the sky. In the northern hemisphere, stars near the north celestial pole helped indicate direction. Polaris was useful in some periods, though its position changed slowly over centuries. Sailors also observed the sun, prevailing winds, waves, birds, watercolor, and cloud patterns. No single sign guided every voyage. Mediterranean sailors could follow coastlines and known landmarks. In open water, experience with seasonal winds and celestial patterns became especially valuable. Across the Pacific, navigators developed highly sophisticated traditions. They read star paths, ocean swells, winds, birds, and the behavior of distant clouds. This knowledge was often preserved through teaching, memory, chant, and repeated travel. It did not depend on written maps alone. In the Indian Ocean, monsoon wind patterns supported long-distance exchange. Sailors learned when winds would carry ships outward and when they would reverse. Ancient navigation was not perfectly accurate by modern standards. It was a practical science built from observation, memory, and careful adaptation. A navigator did not need to understand the modern physics of Earth's rotation. The sky itself offered a dependable pattern for those who studied it patiently. You can imagine a dark sea under countless stars. The ship moves slowly, while the horizon remains calm and open. The measurement of time also began with repeated patterns in light and shadow. Early sundials turned the movement of the sun into a visible daily rhythm. A simple upright object casts a shadow that changes direction and length. By marking these changes, people could divide daylight into useful intervals. Ancient Egyptian shadow clocks used bars and raised crosspieces. Their orientation changed during the day as the sun moved across the sky. Greek and Roman sundials appeared in many forms. Some were carved into stone surfaces shaped to match local latitude and expected use. Seasonal changes made timekeeping more complicated. In some systems, daylight was divided into 12 hours, regardless of the season. This meant a summer hour could be longer than a winter hour. The hour was a flexible portion of daylight rather than a fixed modern unit. Sundials worked only when sunlight was available. Indoors, at night, or beneath heavy clouds, another method was needed. Water clocks measured time through the controlled movement of water. In a simple outflow clock, water escaped through a small opening in a marked container. As the level fell, the markings indicated passing intervals. In an inflow clock, rising water inside a vessel served the same purpose. Egyptians used water clocks at least by the 2nd millennium BCE. Greek engineers later developed more elaborate versions with floats, dials, and mechanical displays. The flow was difficult to keep perfectly constant. Water pressure changed as the level changed, and temperature could affect performance. Engineers experimented with vessel shape and regulating systems. Their goal was not perfect atomic accuracy, but reliable time for ceremonies, speeches, work, and observation. Some clocks became theatrical machines. Moving figures, bells, or indicators could be powered by water and hidden mechanisms. These devices brought together craft, measurement, and quiet entertainment. They turned invisible time into flowing water and gentle motion. There is no need to measure the minutes passing tonight. The water may fall at its own pace while you rest. Calendars extended the same careful observation across months and years. Ancient communities watched the moon, the sun, stars, floods, and seasonal changes. Lunar months followed the repeating phases of the moon. Solar calendars tracked the yearly cycle of seasons more directly. Because lunar months do not fit evenly into a solar year, many cultures added extra months or adjustments. This kept festivals and farming seasons from drifting too far. Egyptian calendars included a year of 12 30-day months, followed by additional days. Observations of the Nile and stars also helped organize the year. Babylonian astronomers kept detailed records of celestial events. Their mathematical methods supported calendars, eclipse predictions, and long-term astronomical study. In ancient China, Calendars combine lunar months with solar seasonal markers. Official calendar making became closely connected with agriculture and administration. Mesoamerican civilizations developed several interlocking calendar systems. These tracked ritual cycles, solar years, and long historical periods. Calendars were practical technologies of coordination. They helped communities agree when to plant, gather, travel, celebrate, or prepare for seasonal change. They were also never completely separated from culture and belief. The sky was measured through the meanings people gave to recurring time. Let the months and seasons turn quietly in the background. You do not need to know where one ancient year ends and another begins. For now, the glass furnace dims, the harbor settles, and the water clock continues its soft descent. Above them all, the stars remain patient and unhurried. In a quiet room in ancient China, a bronze vessel stands beneath the light of an oil lamp. Around its surface, sculpted dragons face outward in several directions. This instrument is associated with Zhang Heng, a scholar and engineer of the Eastern Han Dynasty. Historical records describe it as an early device for detecting distant earthquakes. The original instrument has not survived. Modern reconstructions are based on written accounts, so researchers are still studying its exact internal mechanism. According to the descriptions, ground movement caused a hidden system to release a small metal ball. The ball fell from one dragon's mouth into a waiting container below. The direction of the released ball may have indicated where the disturbance originated. This could alert officials even when local shaking was faint. The instrument did not measure earthquake strength like a modern seismometer. Its purpose was more likely to detect that a significant distant event had occurred. Several possible internal designs have been proposed. Pendulums, balanced rods, and other sensitive mechanisms may explain how motion triggered the release. No reconstruction can yet be confirmed as identical to Zhang Heng's device. Still, the historical description reflects careful thinking about movement, direction, and hidden forces. Imagine the bronze dragons resting silently around the vessel. Nothing moves now, and the room remains calm beneath the evening sky. There is no need to solve the mechanism tonight. You can let the unanswered details remain soft and distant. In another workshop, plant fibers soak in a shallow container of water. They will eventually become thin sheets strong enough to carry writing. Paper developed in ancient China through a long process of experimentation. Traditional accounts connect improvements in papermaking with Kai Lun during the Eastern Han period. Paper-like materials existed before his lifetime. Archaeological discoveries suggest that early forms were already being produced from plant fibers and discarded textiles. Bark, hemp, rags, and other fibrous materials could be softened and broken apart. The prepared pulp was suspended in water and lifted on a fine screen. As the water drained away, a thin layer of tangled fibers remained. Pressing and drying transformed this fragile layer into a usable sheet. The fibers bonded through their natural structure rather than weaving. A relatively small amount of raw material could create a broad writing surface. Paper was lighter than wooden or bamboo slips. It was also more flexible and often easier to store, carry, and produce in larger quantities. Its spread did not happen immediately. Papermaking knowledge moved gradually through regions, trade routes, workshops, and changing political worlds. Different communities adapted the process to local plants and water conditions. Even small changes in beading, sizing, drying, and polishing affected the finished sheet. Some paper was smooth enough for fine calligraphy. Other sheets were made for wrapping, records, religious texts, household use, or practical administration. The process required patience more than dramatic machinery. Fiber, water, a screen, pressure, and time worked together in a quiet sequence. You can picture the fresh sheets drying against a wall. Their pale surfaces move slightly in the evening air. Once writing surfaces became more available, people continued searching for faster ways to reproduce words and images. Early printing methods grew from older traditions of seals, stamps, and carved impressions. In China, woodblock printing became an important technique. A craftsperson carved a complete page of reversed characters into the surface of a wooden block. Ink was applied to the raised areas. Paper was then pressed or rubbed against the block, transferring the page in a single impression. Carving required concentration and skill. One mistake could damage a character, though small corrections were sometimes possible. Once completed, the same block could produce many copies. Religious texts, calendars, images, practical guides, and literary works could circulate more widely. The oldest surviving printed objects do not mark the first moment printing began. Earlier examples may have decayed, been reused, or remained undiscovered. Movable type appeared later in China. Individual characters could be arranged, inked, printed, and potentially reused for another page. Bai Sheng is associated with an 11th century system using ceramic type. Because written Chinese contains many characters, organizing and selecting type presented practical challenges. Wooden and metal movable type were also developed in East Asia. Different printing systems remained useful for different kinds of texts and production scales. Printing was not one invention that instantly replaced handwriting. Manuscripts, block printing, and movable type existed together for long periods. Each method offered its own balance of labor, flexibility, cost, and durability. Technology often grows through overlapping practices rather than sudden disappearance. There is no need to read the pages appearing tonight. Let the inked characters pass gently beyond your attention. In the Mediterranean world, gears continue turning inside clocks, instruments, and small mechanical devices. A gear transfers motion through teeth placed around a rotating wheel. Two gears of different sizes rotate at different speeds. Their relationship allows movement to be slowed, accelerated, reversed, or redirected. Ancient Greek engineers described mechanical systems using gears, pulleys, screws, levers, and air pressure. Some were practical, while others demonstrated scientific principles. Ctesibius of Alexandria explored water clocks, pumps, and devices using compressed air. Much of his work is known through later writers, rather than surviving machines. Philo of Byzantium and Hero of Alexandria also described mechanical inventions. Their texts include fountains, automatic doors, measuring instruments, and theatrical devices. Some machines used falling weights or flowing water as a source of power. Ropes, axles, gears, and valves controlled the sequence of movement. A temple door could appear to open by itself after a fire was lit. Heat expanded air, moving water into a container that pulled hidden ropes. To an observer, the motion may have seemed surprising. Yet it depended on understandable relationships between heat, pressure, weight, and balance. Hero also described a small steam-driven sphere called an eolipile. Steam escaped through bent tubes, causing the sphere to rotate. It demonstrated that heated water could produce motion. There is little evidence that it became a major source of industrial power. A demonstration can reveal an important principle without immediately transforming society. Materials, costs, labor systems, and practical needs all shape whether an invention spreads. Ancient mechanical knowledge was real and often ingenious. It was still limited by the tools, energy sources, manufacturing precision, and economies of its time. You can let the gears turn without following their purpose. Their motion is slow, regular, and almost silent now. Beneath some Roman houses and public baths, warm air moved to hidden spaces. This heating system is commonly known as the hypocaust. A furnace burned outside or beside the heated rooms. Hot air traveled beneath raised floors supported by many small brick or stone pillars. In some buildings, hollow tiles carried warmth upward through the walls. The heated surfaces slowly warmed the rooms above. Bath complexes used different temperatures for different spaces. Visitors could move between warmer rooms, hot rooms, and cooler areas. Operating such systems required fuel and constant labor. Workers tended fires, removed ash, and managed airflow through the structure. Hypocausts were therefore more common in wealthy homes and public facilities than in ordinary households. They were effective, but not simple or inexpensive. Similar ideas appeared in other regions. The Korean ondol tradition directed heat from a fire beneath stone floors through horizontal passages. Early forms developed over long periods. Warm floors became especially suited to rooms where people sat or slept near the ground. In northern China, heated platforms known as kangs also used channels carrying hot gases beneath a raised masonry surface. Cooking fires could provide both food and warmth. These systems turned waste heat into comfort. Their designs connected architecture, daily habits, climate, and available fuel. Imagine a room warmed gently from below. Beyond its walls, the night is cold, but the stone floor holds the memory of the fire. The quiet workshops of the past will keep moving softly in the background. Paper dries, gears turn, and warm air travels beneath sleeping rooms. At the edge of an ancient river, a wooden wheel turns with the steady pressure of flowing water. Its paddles rise and fall beneath the fading evening light. Water power allowed people to use a moving stream as a source of mechanical energy. Instead of lifting or grinding entirely by hand, they could let the current perform part of the work. Ancient water wheels appeared in several forms. Some turned directly in the current, while others received water from a channel above or beside the wheel. As the wheel rotated, its axle could turn a millstone. Grain placed between the stones was slowly crushed into flour. The speed depended on the water supply, wheel design, and weight of the machinery. Millers learned to adjust gates and channels to control the flow. Greek and Roman writers described water-powered mills. Archaeological remains also show that some installations were larger than a single village workshop. At Barbegal in southern France, Roman engineers built a complex of water mills on a hillside. Water descended through a sequence of wheels arranged in parallel rows. Researchers are still studying the exact operation and output of the site. The remains suggest an organized system capable of producing flour on a substantial scale. Water power was useful because a river could work for long periods. It still required maintenance, suitable terrain, and protection from floods or drought. Wooden gears transferred motion from the wheel to other parts of the mill. Their teeth had to be shaped carefully and replaced when repeated pressure wore them down. Inside the building, flour dust settled on beams and stones. Outside, the stream continued moving with little concern for the work it supported. You can let the wheel turn without counting its rotations. The river will carry the old mechanism gently through the night. Wind also offered a source of power where moving water was unavailable or unreliable. Early wind-driven machines appeared in regions with regular seasonal winds. Clear evidence for vertical axis windmills comes from early medieval Persia. Their sails were arranged around an upright shaft inside a partially enclosed structure. Wind entered through openings and pushed the sails in one direction. The turning shaft could operate millstones or help lift water. These machines were shaped by local conditions. Dry landscapes, grain production, irrigation needs, and strong winds all influenced their development. The history of very early wind power remains partly uncertain. Written accounts and archaeological evidence do not always preserve every stage of experimentation. Later windmill traditions developed in other regions with different designs. Horizontal axis mills became especially important in parts of Europe. Ancient and early medieval technologies often overlapped in time. A useful idea could appear gradually, change form, and spread through many generations. For tonight, imagine only the soft movement of cloth or reed sails. The wind passes through them and continues across the dark plain. In a smaller workshop, a craftsperson prepares a lock for a wooden door. The mechanism is simple, but it protects food, tools, records, or private rooms. Some of the earliest known locks come from ancient Egypt and Mesopotamia. They often used wooden pins that dropped into holes inside a bolt. A large key lifted the pins to the correct height. Once raised, the bolt could slide and the door could open. This pin-based principle has a distant relationship to some later lock designs. The materials and shapes changed, but controlled alignment remained central. Ancient keys could be surprisingly large. Some had to reach through an opening in the door and lift hidden pins from below. Greek locks included various bolt and latch systems. Roman metalworkers later produced smaller iron and bronze locks with more compact keys. Some Roman keys were shaped as rings. A person could wear the key on a finger while keeping it close throughout the day. Warded locks used internal barriers that blocked an incorrect key. Only a key with the proper shape could pass the obstructions in turn. These devices did not provide perfect security. Like modern locks, they balanced convenience, materials, cost, and the skill of anyone attempting to bypass them. Doors themselves were also carefully engineered. Wooden leaves turned on pivots, hinges, or sockets fitted into thresholds and lintels. Large temple doors could be extremely heavy. Metal fittings reduced wear, while balanced construction helped the doors move more smoothly. Bolts, bars, seals, and guarded entrances added additional layers of protection. Security was a system rather than a single object. There is no need to wonder what lies behind every ancient door. The key may rest quietly beside the lamp while the household sleeps. In another room, bronze instruments are arranged beside folded cloth and small ceramic containers. Ancient medicine depended on observation, inherited knowledge, and practical tools. Medical traditions developed independently and through exchange across Egypt, Mesopotamia, Greece, Rome, India, China, and many other regions. Surviving texts describe treatments using diet, rest, plants, minerals, massage, bathing, and physical procedures. Their effectiveness varied greatly. Ancient healers sometimes recognized useful patterns. They also worked within cultural theories that do not match modern biology. Archaeologists have discovered scalpels, probes, forceps, needles, hooks, spoons, and other instruments. Many Roman examples were made from bronze or iron. Their forms suggest procedures involving wounds, teeth, eyes, bones, and childbirth. The same tool could serve several purposes depending on the practitioner. Ancient Indian surgical traditions are described in texts associated with Sushruta. These writings discuss instruments, training, wound care, and reconstructive techniques. The surviving manuscripts were copied over long periods. Scholars continue studying how the text developed and how closely written procedures reflected everyday practice. In ancient China, acupuncture traditions gradually formed through changing medical theories and clinical experience. Early needles were made from stone, bone, or metal. The exact history is complex, and modern interpretations should not be projected too simply onto ancient practice. Medical systems changed across centuries and regions. Egyptian medical papyri contain practical observations alongside ritual elements. Some passages describe injuries with careful attention to symptoms and likely outcomes. This mixture was common in ancient healing. Technical knowledge, spiritual belief, household practice, and formal medicine were often closely connected. Pain control and infection remained serious limitations. Even skilled procedures carried risks that modern sanitation and anesthesia have greatly reduced. Still, the surviving instruments show precision and thoughtful design. Their makers understood grip, reach, sharpness, balance, and the needs of a careful hand. Let these tools remain untouched on the table tonight. The room is calm, and no treatment is needed. Across the workshop, a bronze mirror reflects the flame of an oil lamp. Its polished surface was created through patient grinding and finishing. Mirrors in ancient Egypt, Greece, Rome, China, and other cultures were often made from copper or bronze. Some were backed with decorated handles or carved supports. The metal surface had to be smoothed repeatedly. Fine abrasives removed scratches until the reflection became clearer. Glass mirrors also existed in antiquity, though they were less common and often small. Metal or dark backing could help a glass surface return an image. Polishing was a technology used far beyond mirrors. Stone, metal, wood, ivory, and glass all required different abrasives and finishing methods. Craftspeople understood materials through touch and repeated practice. They knew when a surface was nearly complete by its sound, resistance, and appearance. Nearby, A lathe may have helped shape wooden or bone objects. Early lathes used cords to rotate a workpiece back and forth. One worker might pull the cord while another held the cutting tool. Later bow lathes allowed a single craftsperson to create repeated rotation. The motion was not continuous, like a modern electric lathe. Cutting occurred during the useful direction of each turn. Even so, the tool produced regular curves and balanced forms. Bowls, handles, furniture parts, and small objects could be shaped with impressive consistency. A drill could also be powered by a bow. A cord wrapped around a shaft caused it to spin rapidly as the bow moved from side to side. Bow drills were used in woodworking, bead making, stoneworking, and fire starting. Their effectiveness depended on the drill point and abrasive material. These tools transformed a simple pulling motion into quick rotation. The principle was elegant, compact, and easy to repair. The old workshop is almost silent now. Only the bowstring moves softly, then becomes still beside the finished piece. There is no need to remember each lock, instrument, wheel, or tool. You can let them rest where their makers left them. The windmill turns beyond the fields, the watermill follows the river, and a polished mirror holds one last quiet trace of lamplight. Beyond the workshop, a narrow canal carries water toward fields arranged in long, quiet rows. Small gates divide the current and guide it toward different crops. Ancient irrigation depended on more than canals alone. Farmers needed ways to raise water, control its direction, and share it across changing seasons. In Mesopotamia, communities built networks of canals between the Tigris and Euphrates rivers. These systems supported farming in landscapes where rainfall was often limited. The same canals could also create new problems. Poor drainage sometimes allowed salts to accumulate in the soil and reduce its fertility. Ancient administrators recorded fields, harvests, and water obligations on clay tablets. Irrigation became connected with measurement, labor, law, and local cooperation. Along the Nile, another device helped lift water from low channels. The water wheel known as a noria carried containers around its rim. As the wheel turned, the containers filled near the bottom. They emptied into a higher channel when they reached the top. Some wheels were moved by flowing water. Others depended on animals walking slowly in a circle to turn connected gears. Water-lifting wheels appeared in several regions and changed over time. Their exact origins are difficult to trace because wooden machinery rarely survives. Archaeologists therefore study channels, wheel pits, ceramic containers, written accounts, and later examples. Each kind of evidence reveals only part of the design. Imagine the soft creaking of a wooden axle beside the river. Water rises in small amounts, one container after another. There is no need to measure how much reaches the field tonight. The crops wait quietly beneath the stars. Farther east, underground channels carried water across dry landscapes. These systems are often called quanaughts, though regional names and forms varied. A qanat gently sloped from an underground water source toward fields or settlements. Gravity moved the water without exposing most of it to the hot surface. Workers dug a line of vertical shafts along the route. These openings provided access for excavation, ventilation, repair, and removal of soil. The tunnel had to descend carefully. Too steep a slope could damage the channel, while too little slope might stop the water. Qanat technology became especially important in ancient Iran and later spread widely. Similar underground water systems also appeared in other dry regions. Construction required an understanding of terrain and groundwater. It also required courage, organization, and long experience working beneath the earth. The exact history of individual quanates is sometimes uncertain. Many were repaired and extended so often that their earliest sections are difficult to date. Some continued serving communities for centuries. Their endurance came from maintenance rather than from remaining unchanged. Below the sleeping landscape, the water moves almost silently. Only the round shafts above reveal the hidden route. Ancient builders also learned to store water for times when rivers and rains were less dependable. Cisterns were carved from rock, lined with plaster, or built beneath courtyards. Roofs and paved surfaces could direct rainfall into these containers. Settling chambers helped reduce mud and debris before the water entered storage. Waterproof plaster was essential. Lime-based mixtures were applied in layers to prevent valuable water from escaping through cracks. In parts of India, builders created step wells and stepped reservoirs. Long stairways allowed people to reach the water as its level rose and fell. Many surviving monumental step wells belong to later historical periods. Their designs grew from older traditions of wells, tanks, and managed water storage. Water structures were practical, but they could also become social and ceremonial spaces. People gathered there to collect water, rest, talk, and travel. Technology often became part of architecture and daily life. A reservoir could be both an engineering solution and a quiet center of community. Let the stone steps descend gently into shadow. The water below is dark, cool, and still. In another ancient town, workers mix lime plaster for walls and floors. The material begins with limestone heated inside a kiln. Heating drives away part of the stone's natural composition and produces quicklime. Adding water creates a softer material that can be mixed with sand. As lime plaster dries, it slowly reacts with air and hardens. Ancient builders used it to cover rough masonry and create smoother, brighter surfaces. Plaster could protect walls from weather and provide a base for painting. In water systems, special mixtures help resist moisture. The heating of limestone required fuel and careful control. Kilns had to reach high temperatures and remain hot for many hours. Brick making also transformed earth through fire. Clay was shaped, dried, and sometimes fired in kilns to create a harder building material. Sun-dried mud bricks were common in many dry regions. They required less fuel and could provide excellent insulation when protected from heavy rain. Fired bricks were more durable around water, heat, and exposed surfaces. They were widely used in drains, floors, walls, furnaces, and monumental buildings. The Indus Valley cities are known for bricks made in consistent proportions. Standard sizes simplified construction and helped courses fit together neatly. In Mesopotamia, stamped bricks sometimes recorded the names of rulers or building projects. Bitumen could serve as a waterproof adhesive in selected structures. Roman brickmakers marked some products with workshop stamps. These marks now help archaeologists study production, trade, and building dates. Each brick looks simple when viewed alone. Together, Thousands could form arches, baths, warehouses, drains, and entire neighborhoods. You can let the kiln cool slowly now. The final bricks remain warm beneath a thin covering of ash. Above the town, builders prepare the wooden framework for a vaulted ceiling. Curved construction allowed them to roof spaces wider than ordinary beams could easily span. A barrel vault extended the shape of an arch along a continuous length. A groin vault formed where two barrel vaults crossed. Roman architects used vaults in baths, halls, storage buildings, and underground spaces. Concrete and brick made many large curved interiors possible. Temporary wooden centering supported the structure during construction. Once the masonry or concrete became stable, the framework could be removed. Domes carried the same curved principle around a central space. Their weight descended through the surrounding walls and supports. Builders reduced weight in several ways. They could use lighter materials higher in the structure or create recessed panels within the interior surface. The dome of the Pantheon in Rome remains a famous example. Its concrete composition changes from heavier materials below to lighter aggregates above. The central opening, called an oculus, reduces weight and admits daylight. Rain can enter, so the floor includes subtle drainage arrangements. Researchers continue studying Roman construction sequences and material choices. Surviving buildings preserve evidence, but they do not answer every practical question. Elsewhere, corbelled roofs were made by placing each stone course slightly inward. The sides gradually approached until the gap could be covered. Corbelling does not create a true arch. It still allowed builders in many ancient cultures to roof chambers using carefully balanced stone. Post and lintel construction offered another solution. Vertical supports carried horizontal beams made from timber or stone. Greek temples refined this system into highly ordered architectural forms. Columns, capitals, beams, and decorative elements followed carefully planned proportions. The appearance of perfect regularity often required subtle adjustments. Columns might swell slightly near the middle or lean inward by a very small amount. These refinements were not hidden, supernatural knowledge. They were the result of skilled designers observing how large structures appeared to human eyes. Temples and monuments were also rarely built by one isolated genius. Quarry workers, haulers, carpenters, masons, sculptors, metalworkers, and planners all contributed. Their tools were simple compared with modern machinery. Their coordination, accumulated knowledge, and patient labor made difficult construction possible. If your thoughts have begun to wander, you may let them wander farther. Nothing in these ancient buildings needs to be completed tonight. The canals continue toward the fields, the cisterns hold their cool water, and the empty wooden framework waits beneath the stars. In the hills beyond an ancient settlement, miners follow a narrow vein of copper beneath the earth. Their lamps burn softly against walls marked by stone and metal tools. Ancient mining required knowledge of rocks, water, ventilation, and underground support. Workers learned to recognize the colors and textures that suggested useful ores. Some deposits could be gathered near the surface. Others required shafts and tunnels cut deeper into hillsides. Stone hammers, antler picks, wooden wedges, and later metal tools helped loosen the rock. Fire was also used in some places to weaken difficult surfaces. In a method called fire setting, workers heated a rock face and allowed it to crack. Water may sometimes have been used to cool the stone rapidly. The broken material could then be removed more easily. This technique was effective, though smoke and heat made underground work difficult. Timber supports protected selected tunnels from collapse. Small passages reduced the amount of stone that had to be removed. Water entering a mine created another challenge. Buckets, drainage channels, screws, and lifting wheels could help keep working areas dry. Roman mines sometimes used sequences of water wheels arranged at different heights. Each wheel raised water toward the next level. The wooden machinery has usually disappeared. Archaeologists identify it through surviving parts, cuttings, and traces left inside the mine, or brought to the surface still required preparation. Workers crushed, sorted, washed, and roasted material before smelting could begin. Different ores demanded different treatments. Ancient metal production grew from long experience with local geology and furnace behavior. There is no need to descend into the tunnels tonight. You may remain above, where the cool air moves gently across the hillside. Near the mine, charcoal makers prepare fuel for the furnaces. Ordinary wood burns too quickly and contains too much moisture for many high-temperature processes. Charcoal is produced by heating wood with only a limited supply of oxygen. Much of the water and volatile material escapes, leaving a carbon-rich fuel. Ancient charcoal was often made in covered pits or carefully built mounds. The fire had to smolder slowly rather than burn openly. A charcoal burner watched the smoke and adjusted small air openings. Too much oxygen could consume the entire pile. When the process ended, the mound cooled before it was opened. Dark, lightweight pieces of charcoal remained inside. This fuel could reach higher and more controllable temperatures than untreated wood. It supported metalworking, pottery, glassmaking, and lime production. The demand for fuel also affected surrounding landscapes. Large industries required careful access to woodland and repeated supplies of timber. Ancient production was therefore connected to forests, transport, labor, and seasonal planning. A furnace depended on far more than the ore placed inside it. Imagine the charcoal mound resting under a layer of earth. A thin line of smoke rises quietly into the evening. In a pottery workshop, a wheel turns beneath the hands of a craftsperson. Wet clay rises from a low shape into the walls of a vessel. The potter's wheel allowed symmetrical forms to be produced with speed and control. Early wheels developed gradually from turntables used to rotate clay during shaping. A heavy lower wheel could store momentum. The potter turned it by hand, foot, or assistance from another worker. As the clay rotated, gentle pressure shaped the surface evenly. Small changes in finger position altered the width, thickness, and curve. Clay had to contain the right amount of water. If it was too dry, it resisted shaping, while too much water weakened the walls. After forming, vessels dried slowly before firing. Rapid drying could create cracks as moisture left the clay unevenly. Kilns gave potters greater control than open fires. Their enclosed chambers concentrated heat and protected vessels from direct flames. Some kilns separated the fire from the pottery with a perforated floor. Hot gases rose through the chamber while ash remained mostly below. Airflow influenced both temperature and color. Iron-rich clay could become red in an oxygen-rich atmosphere and darker when oxygen was restricted. Ancient potters learned to read flames, smoke, and the color of the kiln interior. They controlled firing without electronic sensors. Glazes added a glass-like coating to ceramic surfaces. Minerals in the glaze melted and fused during firing. In ancient Egypt and the Near East, craftspeople also produced faience. This material was made mainly from crushed quartz with a bright glazed surface. Blue and green faience objects reflected colors associated with water, vegetation, and light. Beads, tiles, vessels, and small figures were made from it. The exact recipes and firing methods varied. Modern experiments help researchers understand how different mixtures produce their vivid surfaces. Pottery rarely survives as a complete vessel. Broken fragments are far more common and extremely useful to archaeologists. Changes in clay, decoration, shape, and manufacturing can help date ancient layers. A discarded shard becomes a quiet record of trade and daily life. You can let the potter's wheel slow now. The finished bowl remains centered, smooth, and still. Across the courtyard, fibers are being twisted into thread. Rope and textiles were essential technologies in nearly every ancient society. Flax, wool, cotton, hemp, reeds, grasses, and animal fibers could all be prepared for different purposes. Each material required its own sequence of cleaning and processing. Spindles turned loose, fibers into stronger thread. A small weight called a spindle whorl helped maintain rotation. The spinner drew out fibers, while the spindle twisted them together. The work could be carried almost anywhere and repeated throughout the day. Several threads twisted together formed cord or rope. Opposing twists helped the final rope resist unraveling. Strong ropes supported ships, cranes, wells, bridges, farming tools, and construction. Its importance is often hidden because organic fibers rarely survive. Ancient Egyptian scenes show rope making and textile production. Archaeological finds also preserve fragments from dry, frozen, or waterlogged environments. On a loom, threads running lengthwise formed the warp. Other threads passed across them to create the weft. Vertical looms sometimes used clay or stone weights to keep warp threads tight. Horizontal looms used a different arrangement near the ground. Weavers produced simple cloth, patterned fabric, belts, sails, nets, and household coverings. The same basic principles allowed great variation. Dyes came from plants, minerals, insects, and shellfish. Some colors were easy to produce, while others required long and expensive processes. Indigo created deep blue through a complicated chemical transformation. The cloth could appear greenish at first and turn blue as it met the air. Madder roots produced red tones. Other plants supplied yellows, browns, and softer shades. Tyrian purple was made from certain Mediterranean sea snails. Producing a small amount of dye required many shells and careful processing. The color became associated with wealth because of its cost and labor. Most ancient clothing used more accessible fibers and colors. Textile technology was not merely decorative. Clothing protected people from sun, cold, dust, and wind. Sails captured energy from the air. Nets gathered fish, ropes moved stone, and bags carried grain. The quiet movement of thread supported entire cities and journeys. Much of ancient engineering depended on fibers strong enough to pull, bind, lift, and hold. There is no need to follow each thread through the loom. You can let the pattern form without watching. In an open field, Surveyors stretch a cord between two wooden stakes. Their work begins before the foundations of a road, canal, or building appear. Measuring cords establish straight lines and regular distances. Knots, or marked intervals, provided simple units. In Egypt, specialists, sometimes described as rope stretchers, helped restore field boundaries after the Nile flood. They also assisted with construction layout. A right angle could be created using a cord arranged as a triangle with measured sides. The geometry worked even without modern notation. Builders checked diagonals to test whether rectangular corners were square. Equal diagonals indicated that the shape was properly aligned. For larger landscapes, sighting instruments helped establish direction. Greek surveyors used the dioptra, an instrument with a rotating sight. The dioptra could assist with angles, alignment, and elevation. Later versions became increasingly refined. Roman engineers used related principles when planning tunnels from opposite sides of a hill. Errors still occurred, but careful surveying improved the chance of meeting underground. Ancient tunnels preserved small corrections where teams adjusted direction. These marks reveal both technical skill and the practical limits of measurement. Surveying joined mathematics with patient observation. A line drawn across the earth became a road, wall, channel, or city boundary. The cord may rest now between its stakes. The measurements are complete, and the field is quiet beneath the moon. The mine, kiln, loom, and survey line all grow distant together. Their work continues softly, without asking you to remember how any of it was done. In a quiet courtyard, a narrow beam of sunlight falls across a marked stone surface. The shadow moves so slowly that its motion is almost impossible to see. Ancient astronomers used shadows to study more than the passing hours. Their length and direction also revealed changes in seasons and the position of the sun. A vertical rod used for these observations is often called a gnomon. By measuring its shadow at noon, observers could compare the sun's height across the year. The shortest midday shadows appeared near summer. The longest arrived near winter, when the sun followed a lower path through the sky. Repeated measurements helped identify solstices and divide the year into useful seasonal periods. These observations supported agriculture, ceremonies, travel, and calendar making. Accuracy depended on a level surface, a straight rod, and careful records. Even small errors could change the result. In ancient China, long traditions of shadow measurement supported astronomy and official calendars. Observatories used gnomons of increasing size to improve precision. Greek scholars also studied the relationship between shadows, geography, and the shape of Earth. Eratosthenes is famous for estimating Earth's circumference using sunlight observed in different cities. He compared the angle of a shadow at Alexandria with reports that the sun stood nearly overhead at Syene. From the distance between the cities, he calculated the planet's approximate size. The surviving account leaves some uncertainties about the exact measurements in units. Even so, the result was remarkably close considering the available tools. It was not a guess based on mystery. It came from geometry, observation, distance, and the dependable light of the sun. There's no need to calculate the angle tonight. Let the shadow continue its quiet journey across the stone. At night, the sky provided another kind of instrument. Observers mapped stars into patterns that could be remembered across generations. Different cultures created different constellations from the same sky. These patterns helped organize seasonal knowledge and guide observation. Babylonian astronomers recorded the positions of planets and the timing of eclipses on clay tablets. Some series extended across many years. Their records allowed patterns to emerge slowly. Repetition turned individual observations into a practical body of astronomical knowledge. Greek astronomers later developed geometric models to describe celestial motion. These models were imperfect, but they created systems that could be tested against observations. Hipparchus compiled a star catalog and compared positions recorded at different times. He is also associated with recognizing the slow shift, now called precession. Precession changes the orientation of Earth's axis over very long periods. This gradually alters which stars appear near the celestial poles. Ancient observers did not know the modern physical cause. They could still identify the pattern through careful comparison. In Mesoamerica, astronomers tracked cycles of the Sun, Moon, Venus, and other celestial events. Architecture was sometimes aligned with significant seasonal positions. These alignments were not always exact observatories in the modern sense. Researchers study each site carefully to avoid assigning astronomical meaning without evidence. Some orientations clearly relate to sunrise or sunset on important dates. Others may reflect terrain, ritual practice, urban planning, or several purposes together. The sky was both a scientific reference and a cultural landscape. Ancient technology often worked within both practical and symbolic worlds. You can let the stars remain unnamed now. Their patterns will hold their places without your attention. On a table beneath the open roof rests a bronze ring marked with divisions. Instruments like this helped observers measure angles in the sky. The astrolabe developed from Greek mathematical and astronomical traditions. Later scholars in the Islamic world greatly refined its design and use. A planispheric astrolabe represented the curved sky on a flat surface. Rotating parts allowed users to model the positions of stars and the sun. With the correct plate for location, it could help determine time, direction, and celestial altitude. It could also support teaching and calculation. Most surviving astrolabes belong to later periods rather than classical antiquity. Their principles, however, grew from much older studies of geometry and astronomy. An astrolabe required precise engraving. Circles, scales, star pointers, and rotating plates had to align closely. The instrument did not replace observation. It organized observations into a portable mechanical model. Other angle measuring devices were simpler. Sighting tubes, graduated circles, and marked staffs helped compare the height of celestial objects. In ancient India, mathematical astronomy developed methods for predicting planetary positions and organizing calendars. Later instruments built upon these long traditions. Knowledge traveled through translation and contact. Greek, Persian, Indian, Babylonian, and later Islamic scholars preserved, criticized, and expanded one another's work. Ancient technology was rarely confined within a single border. Ideas moved with merchants, travelers, craftspeople, diplomats, and manuscripts. The bronze ring may remain still tonight. The stars continue their motion whether the instrument turns or not. In a busy administrative room, scribes press small signs into damp clay. Each tablet becomes a durable record once it dries or is fired. Writing itself was an information technology. It allowed quantities, agreements, names, deliveries, and observations to survive beyond spoken memory. In Mesopotamia, cuneiform developed from earlier systems of tokens and marks. A reed stylus produced wedge-shaped impressions in clay. Many tablets recorded ordinary matters. They listed grain, animals, wages, land, debts, and shipments. Others preserved literature, mathematics, medicine, law, and astronomy. The same writing system served both daily administration and long intellectual traditions. Clay was widely available and reusable while wet. A tablet could be smoothed and written again before drying. Once hardened, it could survive fire, burial, and the collapse of buildings. This accidental durability has preserved details that fragile materials often lost. In Egypt, papyrus offered a lighter writing surface. Strips cut from the papyrus plant were layered, pressed, and dried into sheets. The natural juices helped bind the layers. The finished sheets could be joined into long rolls. Papyrus was easier to transport than stone or clay. It was also vulnerable to damp conditions and usually survives best in dry environments. Elsewhere, people wrote on wood, bamboo, bone, shell, leather, palm leaves, bark, metal, and pottery fragments. Materials depended on local resources and purpose. A broken piece of pottery used for writing is called an ostrakon. These inexpensive fragments carried notes, receipts, exercises, and short messages. Writing tools shaped the appearance of scripts. A pointed stylus, reed pen, brush, or carving tool each encouraged different kinds of lines. Ink also required technical knowledge. Carbon-based inks could be made from soot mixed with a binding liquid. Other inks used minerals, plant substances, or metal compounds. Their durability varied according to recipe and writing surface. There is no need to read the records tonight. Let the tablets remain stacked while the scribes put away their tools. Information also traveled through seals. A carved seal pressed into clay created a recognizable image linked to a person, office, or household. Cylinder seals were rolled across wet clay to produce a continuous scene. They were common in ancient Mesopotamia and nearby regions. The designs could include animals, deities, ceremonies, symbols, and inscriptions. Their small size demanded extremely precise carving. Seals helped close containers, secure doors, and authenticate documents. A broken sealing could reveal that something had been opened. This was not security in the modern electronic sense. It was a practical way to make interference visible. Stamp seals worked through a single downward impression. Different regions preferred different forms, materials, and imagery. Carvers used stone, shell, bone, metal, and other materials. Hard stones required abrasives, drills, and long periods of careful work. The seal joined art with administration. A tiny object could carry identity, authority, and legal meaning. Beside it, counters and marked tablets supported early calculation. Ancient mathematics often grew from trade, land measurement, construction, and astronomy. Babylonian mathematics used a base 60 system. Its influence remains in the 60 minutes of an hour, and the division of circles into degrees. Clay tablets preserve multiplication tables, reciprocal tables, geometric problems, and methods for solving practical calculations. Egyptian mathematical texts include problems involving areas, volumes, rations, and construction. Their methods were expressed through examples rather than modern symbolic equations. Counting boards and small tokens made quantities easier to arrange. Later, Abacus traditions developed in several parts of the world. A counting device does not perform thought by itself. It gives the hands and eyes a structured way to represent numbers. Rows, grooves, stones, or beads turn an invisible quantity into something that can be moved. Calculation becomes a quiet physical process. You may let the counters remain where they are. No totals need to be completed before sleep. The gnomon shadow has now reached the edge of its final mark. The scribes have closed their tablets, and the astronomers have lowered their instruments. Above the courtyard, the ancient sky remains wide and patient. Beneath it, numbers, words, and measured angles settle gently into the night. In a quiet market street, a merchant places a bronze weight on one side of a balance. On the other side, grain settles gently into a shallow pan. Balance is transformed, comparison into measurement. A beam resting on a central support showed whether two loads were equal. Ancient Egyptians used balance scales in trade, workshops, and administration. Similar instruments appeared across Mesopotamia, the Mediterranean, South Asia, China, and other regions. Standard weights made exchange more dependable. Their shapes varied, but each represented an agreed quantity within a local system. Some weights were carved from stone. Others were made from bronze, lead, or carefully shaped ceramic material. Their accuracy depended on trust, inspection, and shared standards. A dishonest or damaged weight could quietly distort every transaction. Officials sometimes checked measures used in markets. Written records and surviving weight sets show that measurement was closely connected with law and taxation. The beam itself had to be balanced before use. Unequal arms or poorly placed suspension points would produce misleading results. Small scales measured precious metals, medicines, pigments, or spices. Larger balances handled grain, textiles, and other ordinary goods. The principle remained calm and visible. When both sides rested at the same height, the comparison was complete. You do not need to weigh anything tonight. Let the beam settle slowly until neither side rises. Length also required agreement. Measuring rods, cords, marked staffs, and body-based units helped ancient craftspeople work consistently. A cubit was generally related to the length of a forearm. Its exact value differed between cultures and periods. Standard rods turned this human reference into a fixed tool. Divisions along the rod represented palms, fingers, or smaller units. In construction, even a small difference repeated many times could alter an entire wall. Builders therefore checked tools against trusted standards. Land surveyors used longer cords and chains. Merchants measured cloth with rods or marked counters. Capacity measures were equally important. Baskets, jars, and containers could represent standard volumes of grain, oil, or wine. Ancient economies did not use one universal system. Units changed across cities, kingdoms, and trade networks. Conversion therefore required experience. Scribes and merchants learned relationships between local measures, much as travelers later learned different currencies. A measuring system is more than a number. It is an agreement that allows many people to build, exchange, record, and plan together. The marked rod may rest beside the balance now. The market is closing, and the final jars have been counted. In a workshop nearby, coins lie inside a shallow tray. Their stamped surfaces carry symbols recognizable to people who may never meet one another. Coinage developed in Western Anatolia during the first millennium BCE. Early examples were made from electrum. a natural or prepared alloy of gold and silver. A marked coin offered a convenient piece of metal with an officially recognized weight and value. It reduced, though did not eliminate, the need to weigh metal during every exchange. Minting required prepared blanks, engraved dies, and controlled striking. A heated metal blank was placed between dies and struck with a hammer. The impact transferred images and inscriptions onto both sides. Differences in alignment and pressure make many ancient coins slightly irregular. Coins supported trade, taxation, wages, and political communication. Their images could identify a city, ruler, deity, animal, or local symbol. They did not replace barter or weighed metal everywhere. Ancient economies continued using several forms of payment at the same time. Counterfeiting and clipping were familiar problems. Authorities sometimes changed designs or inspected metal quality to protect confidence. The metal content of coins could also change for economic reasons. A familiar denomination might contain less precious metal than earlier issues. This made coinage a technical and social system. Its usefulness depended upon metallurgy, measurement, authority, and public trust. Let the small coins remain in their tray. No purchase needs to be made before morning. Beyond the market stands a warehouse filled with jars. Their shapes reveal how ancient containers were designed for storage and transport. Amphorae carried wine, oil, fish products, grain, and other goods around the Mediterranean. Their pointed bases were useful for packing inside ships and storage racks. The narrow neck reduced spilling. Handles allowed workers to lift, pour, and secure the vessel with rope. Different production centers made recognizable shapes and fabrics. Archaeologists use these differences to trace trade routes into ancient deposits. Some jars carried painted or stamped marks. These might identify contents, quantity, producer, official inspection, or destination. Ceramic containers were heavy and breakable, but they were made from widely available materials. Their fired surfaces protected many goods reasonably well. Wooden barrels offered another solution in regions with suitable timber and woodworking traditions. Curved staves were held together with hoops. A barrel could be rolled instead of carried. Its rounded body also resisted pressure from liquids stored inside. The Roman world gradually adopted barrels for some products, especially in northern and western regions. Amphorae continued to remain important elsewhere. Baskets, sacks, boxes, skins, and wooden chests completed the ancient packaging system. Each material suited different contents and journeys. Storage was itself a technology. Grain had to remain dry, oil protected from leakage, and fragile goods cushioned against movement. Warehouses used raised floors, ventilation, sealed containers, and careful stacking. Pests, moisture, heat, and fire were constant concerns. There is no need to open every jar tonight. Their contents can remain safe in the cool darkness. At a harbor, workers prepare a device for measuring the depth beneath a ship. A weighted line disappears quietly into the water. The sounding lead was a simple but valuable navigation tool. Marks along the rope indicated depth when the weight reached the bottom. Some lead weights had a hollowed base filled with tallow. Material from the seabed could stick to it. Sand, mud, shells, or small stones offered clues about location. Experienced sailors compared depth and bottom type with known coastal waters. This was especially helpful in fog, darkness, or unfamiliar approaches. A shoreline could remain unseen while the seabed revealed that land was near. Speed through water could also be estimated with simple methods. Later, mariners used log lines with timed intervals, though ancient practices are less clearly documented. Distance at sea was often judged from speed, time, winds, and experience. Such estimates were necessarily approximate. Sailors did not require perfect coordinates for every journey. They needed enough information to avoid hazards and reach familiar routes. Coastal pilots memorized reefs, currents, headlands, anchorages, and seasonal changes. Their knowledge was a living map carried through practice. The sounding line returns slowly from the dark water. Its weight swings once, then rests against the side of the ship. Near the stern, a steering oar guides the vessel. Early ships often used one or more large side-mounted oars rather than a central stern rudder. The steering oar acted as a movable blade in the water. Its angle changed the direction of the ship. Later, stern-mounted rudders developed in different regions. Ancient Chinese ships provide early evidence for central stern rudders. A rudder allowed steering forces to act near the ship's center line. Its design had to match the hull, water conditions, and vessel size. Some Chinese ships also used watertight bulkheads. Internal walls divided the hull into separate compartments. These partitions could strengthen the structure and limit flooding if one section was damaged. Scholars continue studying the development and dating of early examples. Mediterranean builders used different internal arrangements. Ship technologies were shaped by local seas, cargoes, timber, and inherited craft traditions. No single ship combined every useful idea. Designs reflected particular journeys and practical needs. The harbor is still now. The rudder hangs in dark water while the ropes tighten gently with the tide. In another building, cool air enters through a high opening and passes over water. Ancient architects learned to shape airflow for comfort. In hot climates, courtyards created shaded spaces within houses. Openings placed around them allowed air to circulate through neighboring rooms. Thick walls slowed the movement of daytime heat. Small exterior windows reduced direct sunlight while preserving ventilation. In parts of Iran and surrounding regions, wind catchers guided breezes downward into buildings. Many famous surviving examples belong to later periods, though the underlying traditions are old. A wind catcher rose above the roof and faced useful wind directions. Internal shafts directed air toward rooms below. In some systems, air passed near water or cool underground spaces. Evaporation and shaded masonry could reduce indoor temperature. Underground rooms and cellars also took advantage of stable ground temperatures. They protected food, drink, and people from extreme surface heat. In Egypt, porous pottery vessels cooled water through evaporation. A small amount seeped toward the outer surface and evaporated into dry air. Evaporation carried heat away from the remaining water. The method worked best where the air was hot and relatively dry. Ancient cooling was modest compared with modern refrigeration. Yet architecture, shade, airflow, and water could make daily life far more comfortable. The same careful design helped preserve food. Grain stayed longer in dry storage, while sealed jars protected oil and fermented products. Snow and ice were sometimes collected and stored in insulated pits or special structures. Access was limited and depended on climate, labor, and wealth. Persian ice-storage structures, known as yakshals, became especially notable in later historical periods. They combined thick walls, shade, and evaporative cooling. Their development reflects a broader ancient understanding of seasonal storage and passive temperature control. You can feel the room becoming cooler now. Air moves quietly across the floor without any machine demanding attention. As evening deepens, a small lamp is prepared with oil and a twisted fiber wick. The shape of the vessel controls how safely and steadily it burns. Oil lamps were made from clay, stone, metal, and glass. Their forms change across centuries and regions. A reservoir held the fuel. A narrow nozzle supported the wick and limited the exposed flame. The wick drew oil upward through capillary action. As the oil reached the hot tip, it vaporized and burned. People did not describe the process with modern chemistry. They understood how wick thickness, oil quality, and airflow changed the light. Olive oil was common in parts of the Mediterranean. Other regions used sesame oil, animal fats, nut oils, or locally available fuels. Lamps produced smoke and soot, especially when poorly trimmed. Their light was warm but far dimmer than modern electric illumination. Reflective walls, polished metal, and multiple lamps helped brighten important rooms. Most nighttime work still required care and restraint. Lamp molds allowed decorated clay lamps to be produced in repeated forms. Images, patterns, and workshop marks appeared on their surfaces. A humble lamp joined pottery, agriculture, textile fibers, and fire. Several technologies met within one small circle of light. There is no need for the lamp to burn brightly tonight. Its flame can grow lower as the market, harbor, and warehouse settle into silence. The oil lamp now burns lower, leaving a small golden circle across the ancient work table. Around it, rulers, cords, gears, keys, and fragments of polished stone rest quietly together. Some ancient technologies survive almost completely. Others are known only through broken objects, faint tool marks, written descriptions, or structures altered by many generations. Archaeologists study these traces with patience. They compare materials, construction patterns, historical texts, and experiments using tools similar to those available in the past. Experimental archaeology can show whether a proposed method is possible. It cannot always prove that ancient craftspeople used that exact method. A stone may be successfully moved with ropes and sledges in a modern experiment. The original builders may still have chosen a slightly different arrangement. This uncertainty is not a failure of history. It is a natural part of studying people whose voices and workshops have only partly survived. Researchers are still examining how some enormous stones were quarried, transported, raised, and fitted. Several practical explanations may work together rather than one hidden secret. Prepared roads could reduce resistance. Wooden sledges, rollers in suitable conditions, levers, ramps, ropes, and coordinated labor could each contribute. Ramps themselves may have taken many forms. Straight ramps, Turning ramps, internal routes, and temporary platforms have all been proposed for different monuments. The evidence does not support one universal building method. Ancient engineers adapted their plans to local stone, terrain, workforce, and architectural needs. There is no need to choose a single answer tonight. The unfinished questions can remain beside the finished stones. At an Egyptian quarry, a line of workers follows a natural weakness in the rock. Their tools strike with a slow rhythm learned through long practice. At a Greek temple, masons examine the surface of a column drum. Small lifting bosses remain until the stone is safely placed. At a Roman building site, brickmakers, carpenters, lime burners, haulers, and surveyors all contribute separate forms of knowledge. In ancient India, builders raised stone temples through carefully planned courses, joints, platforms, and carved architectural elements. Different regions developed distinct methods and forms. Across Mesoamerica, communities construct pyramids, plazas, roads, reservoirs, and raised agricultural fields. These projects depend on local materials and organized labor. In the Andes, stoneworkers shape blocks for walls that can withstand frequent ground movement. Irregular stones fit together through repeated checking and adjustment. Some Andean masonry uses finely dressed joints without mortar. Other buildings use smaller stones, earth, clay, and practical combinations of materials. The most famous examples should not hide the diversity of ordinary construction. Homes, terraces, storehouses, paths, and canals were equally important technologies. Terraces transformed steep slopes into workable land. Retaining walls held soil, while channels controlled water and reduced erosion. Farmers selected crops suited to different elevations. Storage buildings placed in cool, ventilated locations helped preserve food. Technology was rarely one impressive object standing alone. It was usually a network of skills supporting water, food, shelter, travel, and communication. You can let the monuments fade into the distance now. The smaller workshops and fields remain warm beneath the evening sky. In ancient China, builders joined timber using carefully shaped wooden connections. Mortise and tenon joints allowed beams and columns to meet without relying entirely on metal fasteners. The projecting tenon fitted into a matching mortise. More complex joints could resist movement from several directions. Timber buildings needed maintenance and replacement. Their flexibility could also help them respond to wind and ground motion. Roofway passed through columns and brackets rather than continuous stone walls. Bracket systems gradually developed into highly refined architectural forms. Many famous surviving wooden structures are later than antiquity. They preserve principles shaped through much older craft traditions. Wood rarely survives as long as stone in exposed conditions. This can make ancient timber technology seem less important than it truly was. Scaffolds, roof frames, doors, ships, cranes, wheels, furniture, and tools all depended on skilled woodworking. Even stone monuments require temporary wooden structures during construction. A vanished material can leave behind only sockets, stains, nail holes, or written references. Archaeologists learn to read these absences carefully. Beside the carpenter, a metalworker creates a saw, chisel, or drill point. The toolmaker supports every other craft without appearing in the finished monument. Edges must be sharpened again and again. Handles split, ropes stretch. Wooden teeth wear down, and bearings need lubrication. Ancient technology survived through repair. A device that could be maintained locally was often more valuable than one difficult to reproduce. Broken pottery could be patched with metal fasteners. Worn tools could be reforged, and damaged buildings could receive new layers of plaster. Ships carried replacement rope, timber, sailcloth, and tools. Travelers understood that every working object would eventually require attention. Maintenance rarely appears dramatic in historical stories. Yet it allowed canals to flow, mills to turn, roofs to remain dry, and roads to stay open. The quiet success of technology often belonged to the person who cleaned, adjusted, sharpened, sealed, or replaced one small part. The old carpenter puts down a smooth wooden mallet. The joint fits well enough, and no further correction is needed tonight. In a garden near an ancient house, bees move between flowers and clay hives. Beekeeping was another technology shaped by close observation of living systems. Ancient Egyptian images show people managing hives and collecting honey. Cylindrical clay hives could be arranged in horizontal rows. Honey served as food, medicine, offering, and preservative. Beeswax was useful for lamps, sealants, writing tablets, casting, and surface treatments. The lost wax casting process depended upon wax behaving predictably when warmed. A natural material from a hive helped create detailed objects in bronze. Fermentation also relied upon processes that ancient people could observe without seeing microorganisms. Bread, beer, wine, vinegar, and other foods changed through controlled time and environment. Brewers and bakers preserved successful methods through repeated practice. A portion of an earlier mixture could help begin the next batch. Grain was soaked, ground, heated, filtered, or allowed to sprout according to the desired product. Containers and temperature influenced the result. Ancient people did not understand yeast through modern microbiology. They still learned how to create conditions in which fermentation occurred reliably. Cheesemaking transformed milk into food that could last longer. Salt, draining, pressing, and controlled aging altered moisture and flavor. Drying, smoking, salting, pickling, and storing beneath oil also extended the usefulness of seasonal foods. Preservation was a technology of time. It reduced waste and made journeys, winters, and uncertain harvests easier to endure. Many methods began in ordinary households rather than royal workshops. You can let the bread rise and the jars remain sealed. Their slow transformations require no watching. The lamp has nearly reached the end of its oil. Before it fades, imagine once more the many ancient sounds surrounding this quiet journey. Water moves through stone channels. A wooden gear meets the next tooth with a soft and regular touch. A potter's wheel turns beneath steady hands. A loom draws one thread across another. In a harbor, a rope tightens gently as the tide changes. Above the ship, familiar stars mark a path across the darkness. Deep beneath a warm floor, the final heat of a furnace travels through narrow passages. In another room, water falls slowly inside a clock. None of these technologies appeared from nowhere. They grew from curiosity, need, error, memory, teaching, and countless small improvements. Ancient people were not modern engineers living in an earlier costume. They understood the world through the knowledge and materials available to them. Their achievements do not need myths to become remarkable. Their patience, organization, observation, and craft are already enough. Some questions will remain uncertain. New discoveries may change how researchers understand a tool, workshop, vessel, or building. That continuing study is part of the quiet beauty of archaeology. The past is not silent, but it rarely speaks in complete sentences. Tonight, there is no need to remember every invention. You do not need to hold the dates, names, measurements, or mechanisms in your mind. Let the gears stop wherever they are. Let the roads continue beyond the hills without following them. The aqueduct water can flow on beneath the moon. The old ship can remain safely tied inside its harbor. The workshop doors are closing now, one by one. Tools are returned to wooden shelves. Fires are covered. And unfinished work waits peacefully for another morning. The final lamp becomes smaller. Its warm light rests for a moment upon bronze, clay, glass, paper, wood, and stone. Then even those shapes begin to soften. The ancient world grows quiet, while its patient ideas remain gently in the background. You can allow your breathing to become easy and unmeasured. There is nowhere else to travel, and nothing more to build tonight. The water clock continues without being watched. The stars continue without being named. And as the last workshop fades into the darkness, you may simply rest, while the long and thoughtful history of human invention drifts quietly into sleep.